Hello, welcome back. We're going to go through another application of differentiation. It's called Rolle's theorem to be applied to a real life problem. And let's read the statement of the question. We have the ordering and transportation cost for the components used in the manufacturing process given by this function, C of x. Here, C is the cost of the components, and it's measured in thousands of dollars. In x is the order size in hundreds. So this question is asking us to verify that C for 300 components, so the cost of 300 components, should be equal to the cost of 600 components in dollars. Once we verify that, and the question is asking us to use the Rolle's theorem to find a point C for which the rate of change of the cost is 0. And for us to be able to apply the Rolle's theorem, all the conditions should be met. And we have the function to be continuous on the closed interval and differentiable on the open interval. And we also have the function having the same values at the endpoints of the interval. In other words, we check the continuity and differentiability of this function for the interval 3 and 6, okay, closed or open. And then the third condition is like we want to check that the function attains the same value at the endpoints of the interval. In fact, this condition here, given in the question statement, tells us how the interval is chosen here. Well, our function is the sum of two rational functions or quotients. Remember that rational functions are not even defined for x's that make the bottom of those 0. While x equals 0 makes the first quotient to be undefined, and x equals -3 makes the second quotient undefined. But for all other x's, this function is defined, and those x's are in the domain. Even though we have those numbers not being in the domain, well, those numbers do not belong to this interval, so there's no x, in other words, violating the continuity or differentiability of this function. In fact, this function is differentiable, and we can perfectly use the quotient rule for each piece to take the derivative of that. And as you see, the derivative is not defined for x equals 0 and x equals -3. But again, those points are not in the interval, so we are safe in terms of satisfying the first two conditions of continuity and differentiability of the function. We're going to check if C3 equals C6, and this is a nice task for you to check. So C3 is 10 times 1 over 3 plus 3 over 6, and then C6. All right, here's C6, and turns out to be that both are 5 over 6. So what that means is that C, the cost, is exactly the same for 300 components and 600 components. And now all three conditions of the Rolle's theorem are satisfied. So then we can apply the conclusion of the Rolle's theorem, which is essentially the existence of at least an interior point C in between 3 and 6, for which we have f prime at C to be equal to 0. So Rolle's theorem doesn't tell you exactly what C is. It only says that there is at least one number satisfying this property. So our next task is to find C by setting this equal to 0 and then solve this for x. All right, to solve this for x, we divide both sides by 10 first, okay, so that we get rid of that 10 without expanding this whole thing out. Well, you have -1 x squared plus 3 over x plus 3 squared equals 0. So why don't we add 1 over x squared to both sides of the equation and to set the equality to the equality of two quotients. All right, at this moment we have two quotients equal to each other, so we can apply the cross product here. So one cross product is 3x squared. Let me just write it here. So 3x squared equals x plus 3 quantity squared. And we can go ahead and expand this out. So this is x squared plus 6x plus 9. And then this is 3x squared. And why don't we subtract 3x squared from both sides to get the final equation. So minus 2x squared plus 6x plus 9 equals 0. And here we go, we have a quadratic to solve. So this is a good practice for you on your own. So why don't you use the quadratic formula for a equals -2, b equals 6, and c equals 9. So that's a good practice for you. The application of the quadratic formula yields two solutions. One is 3 plus 3 root 3 divided by 2. The other one is the minus version of that. Okay, so while the minus version is not going to fit in the interval 3, 6 because it's going to be a minus root. You can even use your calculator. But 3 plus 3 root 3 over 2 is going to be in this interval. So I'm going to go ahead and write down that I have only one solution, x, that makes the cost function's derivative to be 0. And this is approximately equal to 4.09. So in other words, remember that x was in hundreds. So for almost like 409 components, the rate of change of the cost function is 0, and that's what exactly the question was asked. And here is the graphical outlook of the cost function. Remember that cost function is in $1,000 in x. The components are in hundreds. So as you see, for almost like 410 components, the rate of change of the cost function is 0 at the cost of like probably around something around like $8,213. You have a horizontal tangent line achieved. And this graph verifies the conclusion of the Rolle's theorem. All right, this is the end of the video. Thanks for watching. I'll see you in another video. Bye.